We are deriving 1D kinematic equations with constant acceleration, part 2. This is going to be kinematic equations 3 through 5 that we talked about in the full lecture, or that you find in the textbook. I want to note something before we start. In 1D kinematics, for a single object moving, there are 6 possible variables. Those variables are the initial position, the final position, the initial velocity, the final velocity, the acceleration, and the time. Now the interesting thing is, usually these two are pooled together as the displacement delta x. So I say 6, the truth is it's more like 5. Usually you will be able to set your origin point xi wherever you want, because we only care about how far you've traveled. So think about it that way. We've got delta x, vi, va, and t. We've got 2 equations we've already worked out. V is equal to v initial plus acceleration times time. And we'll rewrite this actually, because we'll take the xi back over to the other side. Delta x is equal to v initial times t plus 1/2 acceleration times squared. Now, each one of these is actually missing one of the 5 variables that I've just listed above. And let's have a look. This first one is missing delta x. The second one is missing v. And the reason there are 5 kinematic equations is each one of the kinematic equations is eliminating one of those 5 variables. So let's go through this and figure out the other 3. We're going to start with eliminating the initial. Alright, how will we do this? Well, it's pretty easy. Solve equation 1 because it's the simplest equation for vi, and substitute the result into equation 2. And you'll find that this is pretty much the pattern we use constantly here. Alright, so let's do this. Vi will be equal to v minus at. It's a pretty simple rearrangement. Subtract at from both sides. We'll substitute that in. Delta x is equal to v minus at all times t plus 1/2 at squared. We'll distribute the t. We get v final times t minus at squared plus 1/2 at squared. Here we can do 2 over 2 to create a common denominator. So 2 over 2 is 1. It doesn't change the value of minus at squared at all, but it does make it obvious what the result will be when we add those together. We get v final times t minus 1/2 at squared. And that is our equation 3. This one is easy enough to derive that if you already know the first 2, I don't really recommend memorizing it because you can regenerate it very quickly. Okay, we're going to go from there. So let's see. The difficult one is actually eliminating the time. So we're going to go with eliminate a next. And it's going to go pretty much the same way as the last one. Solve equation 1 for the acceleration. And substitute that into equation 2. Alright, this has to be done in 2 steps. So v minus v initial is at, and that means acceleration is v final minus v initial over the time. Alright, substituting that in. Delta x is equal to v initial times t plus 1/2 v minus v initial over t times t squared. We get to do some cancellation there. We get rid of the t. and then we'll distribute what's left. So VIT plus 1/2 V final times t, and then minus 1/2 the initial times t. Okay, we've got these two pieces. They're the same except for the 1/2, so we'll do the same thing with 2/2. Delta x will be 1/2 VIT plus 1/2 V final times t, which we can simplify that. I'll do it as one more step. Pull the 1/2 out in front, VI plus V final. Pull the t out and back. There we have our equation number 4. Okay, so not bad, running just short of 6 minutes to reach this point. We'll see how long it takes to do the 5th one, because the 5th one we have to deal with a quadratic and there's really no way around it. So, final equation. Eliminate the time. Solve equation 1 for t. Substitute that result into equation 2. I'm going to write the whole thing down here. So V final is V initial plus AT. We'll subtract VI over. We'll divide through by the acceleration. And there we have time. Substitute. Delta x is equal to VI times this entire quantity plus 1/2 the acceleration times, and here's what makes this one harder. We've got to square V minus VI over A. Alright, I'm going to give myself a little more space in the next line. We'll distribute the VI across here, so VIV over A minus VI squared over A plus 1/2 A. Let's square this whole thing out. So we'll have V squared minus 2V VI plus VI squared all over acceleration squared. Now we can cancel one of those accelerations. VIV over A minus VI squared over A plus. Alright, let's take that 1/2 and distribute it in. So we'll have V final squared over 2. The 2 will cancel here, so we'll get a minus VI, oops, the A. I need an A back here. VVI over A, then VI squared over 2A. Alright, let's look for things that we can cancel. These look promising. Those are the same thing with opposite signs. We can just get rid of them. Let's see, this has nothing similar, but we do have these which can be added together. So this one's over 2, let's create a common denominator. So we've got more negative than we have positive, the result's going to be negative. So let's take the positive term first. V final squared over 2A, then the result of this is minus VI squared over 2A. The 2A is common, so I think what we want to do here is multiply each side by 2A so we can move it. And we'll get 2A delta x is equal to final velocity squared minus initial velocity squared, and that is the typical form of the 5th equation. I do think this one is harder to derive than all the others. This one is probably worth your time to memorize. The first 2 you can get pretty easily from calculus. This one, it's worth just knowing. 3 and 4, if you can get 1 and 2 quickly or you happen to have them memorized, they're pretty easy to get, so they're not really worth your time too much. Mind you, by the time you're finished with chapter 2 and chapter 4, you may have done enough of these problems you've memorized all 5 of the equations, and that's certainly reasonable. Alright, so that's how you get the 5 kinematic equations that get used all the time for constant acceleration cases. And we'll stop right there.